We will continue with NMR. In NMR, we have already done the basic concepts. What is NMR? What is the principle of NMR? And then the instrumentation, and then the solvents which we can use for NMR spectrum. And now, what are the chemical equivalent and non-equivalent protons? Now, a set of protons having same chemical environment are called equivalent protons, and a set of protons with having different chemical environment are called non-equivalent proton. So the equivalent and non-equivalent protons are different. If the protons are equivalent, they will give a single signal peak, and if they are equivalent, the protons will give different signals. So let us take up examples. Now these are the examples. In this we have example CH3 CBr2 CH3. Now these three protons are attached to the carbon to which bromine are attached. Now similarly, these three hydrogens again are attached to the carbon, this carbon which has two bromine atoms. Now these six protons have similar chemical environment. These three protons or hydrogens have two bromine around it. Similarly, these three protons also have two bromine around it. So these six protons have same environment. So these are equivalent protons. And then all will give a single signal. So all these six protons will give a one NMR signal. Only one NMR signal. Only one peak will be observed like this. Now, and the second example, CH3 CHCl CH3. Now here these three protons are attached to a carbon to which one hydrogen and Cl is attached. Similarly, these three hydrogens again are attached to a carbon which has hydrogen and Cl atom attached. So these six protons, these three and these three, are equivalent protons. So they will give a single signal which is represented here by A. So suppose these six protons give a single signal. Now this proton which is attached to a carbon to which Cl is attached, and to one side CH3 group is attached, to the other side CH3 group is attached. So this proton is having different environment as compared to these three protons. So this proton will give different signal. So let us represent it by B. So this full molecule will have two types of protons, and these protons are non-equivalent protons, and these protons will give two signals. These three terminal will give one signal, and the central hydrogen will give different signal. So there will be there are two kinds of protons. There are non-equivalent protons, and they will give two NMR signal. So similarly, in the third example, we have CH3 CH2 CH2 Cl. Now here we can easily identify these three hydrogens attached to a carbon which has two hydrogens, and this will give different signal. Suppose it is, let us represent it by A, and these two protons which has these three protons on one side and two protons on one side, this will give different signal, and this protons again have Cl on one side and the CH2 group on the other side, this will give different signals. So there are again non-equivalent protons, three types of protons, three kinds of protons, and there will be three NMR signals. So what are the equivalent protons and what are the non-equivalent protons, we can easily identify from the given example, and we know that the equivalent protons give a single signal and the non-equivalent protons give different signals. Here there will be two signals, one due to these terminal hydrogens and 1 due to this, and here there will be 3 signals. So the equivalent or non-equivalent protons give different signals which we can easily make out. Now if we take up this example, in this these two protons, if they are replaced by some other atom, suppose we replace this by another atom Z, and now these two isomers, we can replace this by Z or by this by Z, that this or this by Z. Now these two isomers are called diastereomeric protons, because if they are, because such pair of protons are not equivalent to each other, as their environments are neither identical nor mirror images of each other. So such protons, which when replaced by some other atom and we get two isomers which are neither identical nor mirror images of each other, that is we get diastereomers, then that protons are called diastereomeric protons. Now and thus if we see these two isomers, this part is the identical, this part of both the isomer is identical, and this isomer is the mirror image of each other, that is if this and this are the mirror images of each other, and that is one if we rotate this portion. So this two examples or these two isomers in which these two protons are present, if one is replaced by some other atom, if we get these two isomers which are the diastereomers, then that protons are called the diastereomeric protons. Similarly, if we take up another example, that is this example, in which these two protons are present, and these two protons are called anisotropic protons, which are equivalent to each other and their environments are the mirror images. These two protons, now if we talk about this proton, this proton has a CH3 group on the one side, and on the other side hydrogen is present. And similarly this proton again has one side hydrogen and one side methyl group. So these two, both protons has the same chemical environment. So this will give one signal, both will give one signal, both are equivalent protons. Now in this, these three protons are surrounded by one on one side hydrogen, on the other side CH3. Similarly this are surrounded by one CH3, one side hydrogen. So these are both the protons will give one signal and these will give one signal. There will be two kinds of protons and there will be two signals. Now in this example again, if we see carefully, now this hydrogen has one side Cl, on the other side hydrogen, so it will give different signal. Now in the second proton, one side is hydrogen, other side is hydrogen, same, both side hydrogens are present, but in this one side hydrogen, one side Cl, so this will give a different signal represented by B. And now this third has one on one side hydrogen, one side Cl, this will give another signal, and there will be three kinds of protons and there will be three signals. So such protons are called the anisotropic protons, which are equivalent to each other and as the environments are mirror images of each other. So if we take up these examples, now in this example these three protons have CO group adjacent to it. Similarly this has CO group adjacent to it, so these are the chemically equivalent protons and they will give one signal. Similarly in this, these are attached to oxygen, these 6 hydrogens will again give one signal and these again will give one signal. So these are the chemically equivalent protons and will give one signal. And if we take another examples in this, CH2Cl, and this will give one signal, this will give one signal, there will be two signals. And in this this extreme CH3 groups will give one signal, and this will give one signal, so there will be two signals. And there are non-equivalent protons, and this also non-equivalent protons. And in this there will be three signals, one due to this, second due to this, and third is due to hydrogen. So these are the chemically non-equivalent protons, and these are the chemically equivalent protons. Now, what is the chemical shift? Chemical shift in absolute term is defined by frequency, magnetic field of the resonance expressed with reference to a standard compound which is defined to be at 0 ppm. That is, chemical shift is defined in very simple words. That is, further we define it, but it is the resonance frequency which changes is very low for protons, and scale is made very manageable by expressing it in parts per million. That is, chemical shift is represented by frequency or magnetic field of resonance, and in which the standard reference compound is taken as 0 ppm. But why ppm is used? Because there is a very small change in frequency, resonance frequency or field, and so the scale is made manageable by expressing the unit in ppm, parts per million, and it is independent of the spectrometer frequency. So we define chemical shift as shift in the position of PMR signals resulting through shielding and de-shielding by circulation of electrons in chemical bonds is called chemical shift. It's very important. What is chemical shift? It is the change in the position of PMR signals due to the shielding and de-shielding by circulation of electrons in chemical bond is called chemical shift, and which is field independent, and it is denoted by delta. Chemical shift is denoted by delta, and delta is defined as shift in, mathematically, shift in hertz divided by spectrometer frequency in megahertz, and this is represented in parts per million, ppm. And the units which we generally use is expressed in ppm. For ppm, delta is shift in frequency from TMS, tetramethylsilane, that is reference compound, in hertz divided by frequency of spectrometer in hertz, and if it is in megahertz, then there is no multiplication by 10 to the power 6. If it is in hertz, then into 10 to the power 6, and it is dimensionless and not proportional to H0 or oscillation frequency, and value is same in all different instruments, and it is universal scale in NMR. Higher the value of chemical shift in hertz or de-shielded is the proton. This we can understand further. Lower the value, chemical shift in hertz or shielded is the proton. This we further explain in the figure. That is, this is the chart where the scale for chemical shift is taken, and this is the scale. It starts from 0 to 10 mostly, because mainly the values lie between 0 and 10. Now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now on the scale, this line shows the line of peak of reference compound, that is generally TMS, and as compared to this we plot the signals of other on this scale. In this scale, if the value lies near 0, then it is said to be shielded. The protons which are shielded, that is which have electrons around it, are generally towards 0, and the hydrogens which have less electron density around it have values towards 10, and they are called de-shielded. So the protons which have electrons around it are called shielded, and they show upfield signal, and the protons which have less electron density around it are called de-shielded, and they show downfield signal. That is, downfield de-shielded side is on the left and requires a lower field strength for resonance. They require lower field strength that they get easily resonance, and the upfield shielded side is on the right and requires a higher field strength for resonance. So tetramethylsilane is absorption is used as a reference point, and it is taken as 0 ppm. This is the 0 ppm of the TMS signal, or we can easily show like this. 0 to 10 is the scale, and in this, if with values towards 0, then it is shielded and it is called upfield, and if it is electron density is less, then it is said to be de-shielded, and it will have peak around 10 towards this side, and it is called downfield. So this can easily be said that if it is downfield, it has less electron density or an isotropic effect, electron not oppose the external magnetic field, hence these protons require lower external field to come in resonance. While on high field, that is if they are shielded, more electron density, electron oppose the external magnetic field, hence these protons require higher external field to come in resonance. So next we will continue with other topic in the next lecture. Thank you.